continuing. Let's get started on reviewing for the test. So going over last year's or 2 years ago test. So looking at some of these, and I'll have to make up a new problem fresh that's not on this. Come on, we're waiting for my Word document to open. Okay, of course. And just a handy thing, I don't mind you have to leave the meeting for a phone call, whatever. Just mute yourself. Just make sure you mute yourself. That's all I ask. I understand. Wonderful. It crashed. Let's see if it'll. Okay, so we were. Okay, wonderful. So we were on number 7. What are the pH of the following buffers? So we still need to look up the pKa and pKb for these guys, but we have various buffers here. So how do we treat these guys? So looking up the pKa or pKb. So first thing you do on this test is you'd be state, I got this pKa from the book. I got this pKa from Achieve. I got this pKa from the Wikipedia entry for carbonic acid. Wherever you choose to get it, I really don't care. State where you got it. Problem. So if I think, whoa, where did you get that number? Why is that number so different from my number? I can look up and say, oh, they honestly made a stupid mistake. As opposed to like, no, you're right. Or way wrong. So I look up the Ka of carbonic acid in the back of my book. You get 4.3 times 10 to the negative 7. There's the Ka. So for the Henderson-Hasselbalch, pH equals pKa plus log of A minus over HA. It's just a fancy way of looking at this. I just took this and I took the negative log of that to turn it into here. So I don't care if you use this equation or you use this equation. You'll get the exact same results. So here is my HA. What is your HA to find out? It's the protonated acid. The A minus is just the conjugate base, the deprotonated anion. Now, technically, bicarbonate has another proton it can lose. But looking from here, this guy's 1 proton more. This is 1 proton less. So this guy's going to be our A minus, our base, and this guy's going to be our acid. If I want to use this version, I'm going to say, oh, okay. So Ka is 4.3 times 10 negative 7 times HA, which is our 0.085 divided by our 0.124. So doing that math real quick. .085 divided by 0.124 times 4.3 times 10 to the negative 7. That gives us a H plus of 2.95 2.95 times 10 to the negative 7. Yeah. Which, that's our H plus. Now the question asks, what is our pH? So pH, remember, is going to be negative equals negative log of our H plus, which is 2.95, and 10 to the negative 7. Do the negative log of that. And there's our answer. So we get a net. So this buffer is very, very, very weakly acidic at 6.53. This is not what I'd call a very strong acid, but it is still technically acidic. There's more base, conjugate base than acid, but the amount of protons that get formed in this situation is greater than the amount of hydroxide. So, similar problem, piperidine. Piperidine is a base. This has a Kb. You probably never heard of piperidine before, and that's fine. Now, in fact, my book that I have right now doesn't have piperidine in it. So I'm going to just quickly Wikipedia piperidine. But that's fine. You just state which source you found, and I can check it other places. Here. Dean. Look up KB. You look, if you click on Wikipedia, you look on the properties, you see chemical formula, molar mass, density, melting point, solubility. Well, that's convenient. They give you the pKa. Now, this is a base, so technically, you should be getting the pKb. But they give you the pKa. So with that in mind, we have to be very careful. Notice the pKa is 11.22. Now, with this in mind, pH equals pKa plus log of A minus over A minus over AHA. Okay. Now, you could also look at this as pKa plus log of base over protonated base, which would be the acid, which it's the same thing. This is the conjugate base. This is our acid. This is the base. This is our conjugate acid. They're the same exact equation. It just, this guy's one more negative. This guy's one more positive. This guy's one more negative. This guy's one more positive. Plus 1 is more positive than 0. Minus 1 is less positive than 0. So with that in mind, this guy is our base. This guy is our conjugate acid. So as we plug that in, you could use this. You don't have to have a KB to deal with this. You would just go, oh, I'm log of our base on top divided by our acid on bottom. And because we've set it up like this, this will already give us pH. If we solved it from a KB perspective, you would have had to turn that from POH to pH. But from this perspective, gives us directly pH. So I'm saying 11.22 plus log of 0.35 over 0.28. You do that, you're going to get 11.31.
So for this problem, though, if you use the pKa, which one do you use to find which one do you? Well, I guess they're both the same. They're just acid or base.
So
Both are.
both are the same. Base always, if you're using pKa, it's base over an acid, base over acid. The other equation would just be the inverse. POH equals pKb plus log of acid over base, which equals pKb plus log of, what's it, BH plus over B. So it's the same thing regardless of which way, whether you treat it like this or like this. It's always acid on top, base on bottom when you're dealing with the base, or base on top, acid on bottom when you're dealing with the acid. Because it's all looking at this. It's all coming from this setup. Because clicking over, we're essentially, for the other guy, it's OH minus equals KB times what, like, it would be base divided by BH. So it's coming from that equation, which is why it, so that's acid over base. This is base over acid, which is why they still have the same relationship. They're flipped same way. But as I said, have all the equations in front of you when you work on this test. Don't feel like it's not cheating to have all the equations you could possibly use. Just make sure you label them carefully. This is Henderson-Hasselbalch, which comes from this. But I mean, if you can do this, which comes from our K, which comes from that. This is our starting equation. We've turned it into this for a buffer. And you modify it to get to there for the Henderson-Hasselbalch. But this is our initial starting point. And that's our initial starting point for everything. So it's not magic to get from here to here. It's just the systematic mathematical treatment of separating the variables to solve for the unknown.
And the one other one of the equation is KW equals KB times KA.
Yeah.
Okay, all right, I was making.
So like, let me go ahead and put that one. KW equals H plus.
I don't know what the fuck is happening right now. Oh, you want to see my plan?
Right now, I'm just trying to remind you of all the crazy ass stupid equations we got. So this is our starting equation where the relationship of acid to base goes. Kw, which is 10 to the negative 14th, is equal to the concentration of acid times the concentration of base. And that's also equal to the Ka times the Kb. So the stronger the acid, the weaker the base. So having that and being able to set up a Ka expression is number one skill, most important. From there, it's just a matter of conversion. Okay. I think what, 8, 9, and 10, the last 3 problems. Shouldn't take us too long. 8 is based on the lab that most of you have just done. Following the questions regard iron thiocyanate complex. This is your K equation for this. So ice table. Put in an ice table. I'm going to insert a table in here just so we can see this. Yeah. point. Yeah, that's pretty good. Okay. So got our I, got our C, got our E, got our FE, SCN, and FE, SCN. Okay, looking at this ICE table for this one. Now, how do I know this is an ICE table right off the bat? Words like initially and equilibrium are used. Initially, I have this much iron and this much thiocyanate. At equilibrium, we have this much iron thiocyanate complex. So when I start at a situation at initially, the products are always 0. So remember when we do the ICE table, it's always plus times plus, it's X times the coefficient. Coefficient's 1, it's just 1. Minus X, minus X. And I plus C will give us our E. With that in mind, so if this is 0 plus X, then our X must be 0.00105. So with that in mind, how much thiocyanate must remain? If we have 0.0018 and we've lost 0.00105, we would have 0.00075. Same thing. If I started with 0.0026 and I lost 0.00105, I would have 0.00155. What I've done is I've just taken this number and subtracted this number. Now, with that in mind, our K expression is this. So I'm plugging these 3 numbers into our K expression. So 0.105 divided by 0.00075 divided by 0.00155. We have our K in this problem is 903. Our K in this problem is 903. So 0. 5.
And they're not raised to anything because they have no coefficients.
Yes, because they're raised to the power of 1.
Right.
Because their coefficient is 1. And so I got 903. Now, with this in mind, consider this competing reaction. Iron plus chloride goes to iron chloride. So what would happen to the concentration of iron thiocyanate if you add HCl to solution? So H plus doesn't really have an effect on this, but Cl minus. What you have to think about is this is the common ion effect. This is Le Chatelier's principle in action. If I add chloride, iron is being consumed to form iron chloride complex. Now, with that in mind, if I remove a reactant, iron, if iron concentrations go down, what will happen to the products? Well, if reactant goes down, the reaction will swing left. If it swings left, we lose product to reform and replace the lost reactant. So what will happen to the concentration of iron thiocyanate is it will decrease because we have this competing reaction that is using up the available iron. So we'll get less iron thiocyanate as a result. So FeSCN goes down as reaction shifts left, replace the lost iron. Okay. That one,
Wait, I have a question.
yes.
So for the K, you got 903.22?
Yeah.
Okay, because I'm getting 90.3.
Well, let me double check my math. I could be like way off. Let's see. Let's see. I mean, double check your number of zeros. Say 0.00105. And someone else check me as well. I'm getting 903 again. Double check your zeros. Because there's 3 zeros here, 2 zeros, 2 zeros. Guessing like if you lost a zero somewhere, that's going to be where you where it's going to pop up. I mean, as I said, I've been wrong in the past. We can come back to that. We should have some time. We should have some time. Let's see. Let's just keep moving for now. Following reaction, silver plus ammonia forms silver ammonium complex. Here's your K expression for this. How much silver nitrate, silver ammonia would be present if we have these guys at equilibrium? This was a problem that tripped up a lot of people on the last test. If I have a K expression and I have this guy, so silver ammonia, we'll just go that, divided by, let's put these in parentheses. We'll have enough time to finish this, and silver plus times ammonia squared. Okay. So looking at this, products over reactants. Of silver, we have ammonia squared over silver ammonia. It's not perfect, but it'll do. So if I have two of these guys and it's solving for the third and I have the K expression, I literally can just solve for the unknown. So I'm going to reset this. So K times my silver times my ammonia squared is equal to my silver ammonia complex. So solving for that, this tripped up a lot of people on last test. So 1.7 times 10 to the 7th, e to the 7th, times my 0.0025 times my 0.0035 squared. So plugging that in.
1.49 times 10 to the second.
Oh,
I forgot to square it.
yeah. So you should, I got 0.52. So 0.521 maybe. You want to be, shoot. 0.52. Yeah. So it literally becomes, if I have this, and note, how do I know I don't have to do an ICE table? These are the concentrations at equilibrium. What is the equilibrium concentration of this if these are the equilibrium concentrations of that? So no ICE table needed. No, nothing complicated. I just get those to the other side and solve for the unknown. Get those to the other side and solve for the unknown. So don't overthink that. So now the last problem here, classify the following acids, bases, and Lewis as Lewis acids, Bronson-Laurie acids, Arrhenius acids. Basically, all of the Arrhenius is going to be the most, the least used. Lewis is going to be the most used. Everything is going to be a Lewis. Everything is going to be a Lewis because everything can donate lone pairs or donate. So this guy is going to typically be a base.
Is
This guy's,
Lewis structures are talking about the electrons, and the Bronsons are talking about the protons?
yeah, Lewis acids and bases are going to be ones that donate lone pairs or accept lone pairs. Bronsted-Lowries are ones that donate hydrogen or accept hydrogen. Now, Arrhenius are literally ones that produce hydrogen, H+, or produce hydroxide. So this guy would be a Arrhenius base, but this guy and this guy will be a like Lewis base or Lewis acid, depending. So this guy is going to be, just looking at this, this guy, oxalic acid and cesium hydroxide are the only guys that could be classified as Arrhenius. Because, shoot, what the hell? Arrhenius, by definition, so this guy can donate a hydrogen right there. And that's going to make it Arrhenius. This guy's going to donate a hydroxide right there and it becomes Arrhenius. Now, cyanide is the conjugate base of hydrocyanic acid. So that could easily take a hydrogen. That's going to be a Bronson-Laurie base. Aniline, NH2, can easily accept a proton to become NH3 plus. So that's also a Bronsted-Laurie base. But these guys, zinc and phosphorus and carbon monoxide and borane, do not have a Ka or Kb associated with them. So they are not going to be Bronsted-Laurie, but they're going to be Lewis acids and bases. Now, what classifies these guys as acid and base? You want to draw the Lewis structure and say, how do they have electrons or are they missing electrons? So phosphorus is in group 5. Group 5 means 5 valence electrons. So 3 bonds means 1 lone pair of 2 electrons. This guy is going to be a Lewis base. Zinc, 2+. It's a metal. It's a cation. It is shy of electrons. It's going to be a Lewis acid. Boron, borane, group 3. Group 3, It can make 3 bonds. It has 3 electrons. It made all its 3 bonds. It is shy of an octet. It is going to be a Lewis acid.
Because acid wants to accept electrons?
Gain electrons. And carbon monoxide. You draw the Lewis structure. There's a lone pair on carbon. There's a lone pair on oxygen. They have a lone pair that they can donate. So that is a Lewis base. So when they have a free lone pair that they can willingly donate and they already have an octet, they're typically a Lewis base. If they don't have an octet and they don't have some free lone pairs, they're typically a Lewis acid. So we just have to look through these and we can look on them. Sorry. But so this was the test. There was one problem in here that we skipped because this is something we covered last chapter. Now we're out of time. I don't have enough time to work through a problem. I'm going to quickly work up a problem and post a problem onto YouTube of like an example titration problem. Something that I'll work through one. It's going to be very similar to what you might see on the test. So even though we don't have time to go over here, I'm going to post this and I'm going to post that shortly. So now if you still have questions, you want to work through some homework, come meet me, come to chat with me after class. We'll deal with it. But if not, I'm going to go ahead and post this. This is the old test. So well, I'm going to deal with that, and you should expect to see some emails before too long. Okay. Have a good day. Stop recording.